Hello. No? My name's Guy Harrison. I work for Dell in the Dell Software Group. I'm Executive Director of Research and Development in Dell Software. And today we're going to talk about database performance tuning. So first I'll introduce myself and Dell. So me, I've worked with databases, especially Oracle, since the late 1980s. This is what I looked like when I started working with databases. Databases have made my hair fall out. But when people look at that picture and they think, why did he wear such big glasses? I can tell you why. In the 1980s, Bill Gates, big glasses, right? Founded Microsoft. Michael Dell, big glasses, founded Dell Software. So big glasses means big future. So my advice to you is wear very big glasses. So I've written some books on databases for about 15 years, 4 books, mostly on Oracle, one on MySQL. Whoa. Oh, thank you. This is the latest one, Oracle Performance Survival Guide. This book is translated into Chinese by James Tong. That's his website. It's all in Chinese, so he translates Oracle database things into Chinese. So this is the book translated into Chinese, so you can read it if you need to. Most of this talk is in that book, but you don't need to buy the book. You can contact me. This is my email address. This is a website that I have where I write blogs and talk about databases. And this is my LinkedIn page, Guy Harrison Dell. If you want to join me on LinkedIn, you'd be very welcome. So Dell Software, you've all heard of Dell, right? Dell computers, laptops, servers, so forth. Dell, between 1990 and 2005, Dell became the biggest seller of PCs in the world. The biggest PC company in the world was Dell 10 years ago. But a while ago, Dell decided that to change from just selling PCs to sell software, services and solutions. And so Dell created a software group called Dell Software Group. And in Dell Software Group, we have 1,600 engineers and 2,500 salespeople, and we're growing all the time. So coming to work for Dell in Dell Software is a very good career idea that you might want to consider. I lead the group at Dell for information management. So we develop products like Toad, if you've heard of Toad. That's developed in my group. I live in Melbourne, Australia. This is beautiful Melbourne. That building there is the Eureka Tower. It's the tallest building in the Southern Hemisphere. I work in a little office just there. Can you see the arrow? There. That's my office. Small office. But I can see the big tower. If you want to know how to get to Melbourne, does anyone want to know how to get to Melbourne? Okay, one more thing. I have people who work for me all around the world. In Zhuhai, I have about 65 people in my organisation, and there's 270 people in Zhuhai altogether. And then we have people in Melbourne, California, Europe, and India. So it's a big group all around the world working together to build software. It's very exciting. In Zhuhai, we have, as I said, 273 people. It's the fastest growing office at Dell Software, so we are hiring all the time. Charles here in the front is hiring people right now. People at Zhuhai seem to be pretty happy, and it's a good office and a nice place to work. So, if you want to know how to get to Melbourne from China, just ask Google, right? If you want to know something in Australia, we always ask Google. So if I ask Google, how do I get to Melbourne from Zhuhai, it tells me to do this. It says, first go to Japan, which seems like a funny thing to do, and then cross the Pacific. And can you see here where it says take a jet ski across the Pacific? Do people know what a jet ski is? That's a jet ski. That's how you get across the Pacific according to Google. But it takes a long time, so I recommend you take a plane if you come to Melbourne. Okay, so enough about me. What are we going to talk about today? First, I want to start by talking about how databases work. Then, how to write code, program code, Java, SQL code, that will make the database work well. As I said, not just Java or C#, but also the SQL code. How to reduce contention in the database, bottlenecks, that is. How to tune your I/O, disk I/O, and using solid-state disks, which are an important new way we have to make databases go faster. And we'll talk about each of those in step, and I'll try and go slow so afterwards we can have some questions. So how do databases work? Well, there are different sorts of databases, Oracle, SQL Server, MySQL, but they all work pretty much the same way. The application, the program, sends SQL to the database. The database looks at the SQL, works out how to execute it. It has to compile the SQL. Then it looks for the data inside memory first, and then if it can't find the data in memory, it goes and gets it from disk. So always in databases there are these 4 steps: the application, sending the SQL, looking in memory, looking on disk. So let's look at that again. So if I'm an application, like a Java program, an application server, and I want to talk to the database, I send SQL to the database server. The database server gets the SQL, works out what to do with it, and then looks for the data in memory. And then if it can't find it in memory, then it goes and looks for it on the disk. And the disk is the slowest part, right? Disks are very slow. So that's the thing we want to do last. And then we send the data back to the application. Okay? So because of the way it works, it goes down and then up again. Problems at the bottom can be caused by problems at the top. So it's always best to work down through those layers. Tune the top layer first, because the top layer determines how much load goes on the second layer. Application code first, SQL code, look at the database contention, try and work out how much memory to have, and then tune the disks. Every time, work in those orders. So first, tune the SQL and your application code to make sure that it's doing the right thing with the database, that it's not asking for too much. Then look at the database itself, configure it so that it's letting all those requests go through. Then allocate memory so that the database doesn't have to look on disk, so the database can do as much as possible in memory. And then only when you've done all that will we go and tune the disks, see if the disks are running fast enough and do things to them. Always in these 4 orders. This is the most important slide in the presentation. If you remember this and you don't remember anything else I've said, you will make a good database tuner. But if you come to a database and you start with the disks, you will always be making a mistake, because you'll never be working with the real problem. You'll be working on symptoms and not on the causes of the performance issues. But we will spend, we will go through each of these one by one in the next hour or so. Okay, so how do you tune the application? There are 3 things that we need to do to tune the application. One is we have to tune, or we have to model the data. So the database contains data in tables, and we have to work out how those tables should be structured in order to let the database work effectively. Then we should change our program code, write our program code to put the least load on the database, not to overload the database. And then we need to look at the SQL statements that we write and make sure that they're the right SQL statements, the right SQL that's going to execute effectively. Then when we've done that, we tune contention in the database, and this is mainly locks and another sort of lock called latches. So we'll come back to that, but locking is a big problem in databases. So we need to look at that. Then when we've done that, we'll look at how to get memory and allocate memory so the database doesn't have to go to disk, so that the database can find the data in memory or can do the operation in memory. And then when we've done that, we'll tune I/O, and we do that by using fast disks and by spreading our data across those disks very evenly. And then today, in today's world, we can also use solid-state disks, which means we can get a big performance improvement just by spending some money. So just to illustrate that first problem, what's wrong with this donkey? Is there something wrong with the donkey? No, there's nothing wrong with the donkey. It's the load, isn't it? Someone's put too much on the donkey, and now the donkey's lifted up and can't put its feet on the ground and can't move forward. That's what happens when your application puts too much load on the database. It's not the problem of the database, it's the problem of the application. You can't fix this by fixing the donkey. You can't give the donkey a carrot or, you know, an injection or exercise the donkey and make the donkey go faster. The only thing you can really do is take the load off the donkey. So the first thing in the database is to take the load off the database by looking at the code and the requests that you're making. So we'll spend a lot of time on that and hopefully you'll get some ideas about how to do it. So, application. That's where we start. We make our application put the least load on the database. Just like the donkey, we try and make the application take the load off the database. We make the database work smarter, not harder. So there are three things we can do to tune the application. First, we design our tables and indexes. Then we work on our Java or C# code or Ruby, Python, whatever the program is written in, we change that code. And then we look at the SQL itself and change that. So we'll start with designing tables, which is what we call data modelling. When we start to build an application on the database, what's the first thing we have to do? We have to create some tables, right? The database doesn't have any data in it unless it's got tables, so that's always the first thing. It's very hard to change your tables when you've created them. So if you create your tables and then write some code, SQL code, Java code, reports, and you want to come and change the table later, you'll have to change all the SQL and all the code that looks at those tables. So it's hard to change it later on. You should make sure you get it right first. So the first thing to do when creating table is to start with third normal form. Have you ever heard of third normal form? Some people are saying they have. Third normal form is the starting point of good design for databases. And we remember it by saying the key, the whole key, and nothing but the key. Have you heard that saying? Or the truth, the whole truth, and nothing but the truth? In America they say that a lot. So we want we take all of the redundancy, all of the duplication out of the data model, and we make sure that every row in every column, in every table, can be identified by a key, the primary key, and all of the primary key, not just part of it, and nothing else but the primary key. That's why we say the key, the whole key, and nothing but the key. So third normal form is mainly about not repeating yourself. So let's say I want to create a table to put all of your, if I gave you a test after this, I'm not going to, but if I gave you a test and I wanted to store it in a table, I might create a table like this with your student ID, your name, the name of the test, and the answers in the scores. But that would be a bad design. Why? Because I'd have to repeat your name every time I gave you a new test. And I'd have to repeat the test name for every student. And I'm repeating the answers every time. For there's 12 questions, so I've got 12 answers. But what if I had 100 questions? I'd have to keep adding columns. So we don't want to repeat those things every time, and we don't want to have, we want to make sure that if we add more questions later, that I can still store it in the table. So when we take this table to third normal form, it probably looks like this, 5 tables. So that might seem a little bit complicated, but it's really representing how the data is organised in a way that doesn't repeat anything. And so what we have here is students take tests, so we have a separate test table. Tests have questions, so we have a separate questions table where we put the names of the questions. And students who take tests give answers, so we have another table that has that data in it. Now this is a whole, third normal form is a whole series of lectures and it goes on for a long time. But if you mainly remember that the primary key is important and not to repeat any data, then you probably understand third normal form well enough. When you're picking a primary key for a table, like our students table, you sometimes have a choice between picking something that already exists or creating something new. So if we took the natural key, if we take the student ID that already exists, that's called a natural key. So your student ID or your government ID number, that might be the natural key. And that's what we'd say the primary key is, student card number. An artificial key is one where we just create a number, it doesn't mean anything, and we just give everyone a new number when we create the table. And so we might just create a new column called student ID. So why would we do that? Because you might go to a different university, or you might lose your card and have to get a new number. We don't want to have a primary key that changes ever. So if you're going to pick a column that already exists in the world, make sure it never ever changes. If you think it might change, then you should pick an artificial key, one that you create yourself and you generate the number artificially. When you go and create your tables, don't go too far. So you saw before we created 5 tables for students, but what if we decided that more than one student can live in a house and more than one house can be in the same country? Then we might create 3 tables like this. And it's not wrong, but it's very, very slow, because every time we want to look up your address, we always have to join 3 tables. And joining tables is slow, so we don't want to do it if we don't have to. So be very careful that you don't get carried away with your normalisation and keep creating more tables, more tables, more tables. Create enough tables, but no more. It's judgment, but it's important. So in this case, better to just have one table. It's okay to have the address in the students table, even if there are 2 students with the same address. It probably doesn't matter. Okay. Still on modelling, sometimes we have the situation where we have things called subtypes. So subtypes occur when you've got things that are almost the same. So for instance, in a lot of applications you have customers and you have employees, right? If we have a business, we have 2 types of people. We have people who buy from us and people who work for us. But sometimes a customer can also be an employee, right? You can have an employee that buys a product from the company, and both of them are people, so they've got a lot of things in common. They've got birthdays, date of birth, they have addresses, they're male or female. So they're very similar in some respects. So how many tables should we create if we've got customers and employees? So this is one way that you'll see it sometimes in a data model. You'll see one box, people, with other little boxes inside for different types of people. Customers, employees, maybe students, teachers, whatever the different types of people there are, you might see that. So you could create 3 tables. One table has all the things one table has everything in common for all people. Another table has just things for employees, and another table has just things for customers. Or we could put it all in one table. Or we could have 2 tables, one for employees and one for customers. And there is no right answer for this, but generally speaking, we want to keep the number of tables as low as we can. The more tables we have, the more joins we're going to have. So when you're thinking about how many tables, you generally want to keep the number of tables as small as you can. So in that case, it's usually better here to have 2 tables or 1 table, but not 3 tables. So I would say don't create 3 tables, because if you have 3 tables, then every time you have a customer, you have to join 2 tables. Every time you've got an employee, you have to join 2 tables. If you have an employee who's also a customer, you have to join 3 tables, which is not good. Okay. So a null value Do people understand what a null value is? Probably yes, right? A null value is one that's unknown. If we have a null value, it's not yes or no, it's unknown. We haven't put any data in it. It doesn't mean anything yet. It's normal to create null values, but they have a lot of performance issues. They are very efficient in space. A null value won't take up any space at all in the database. So that keeps the database tables small, which means the database will be fast. But you can't index on a null, which means that when you're looking for something that's null, it's always very slow. So if you've got a null value and you think I might need to look for those nulls, then you shouldn't use a null. You should use some other value. You should say unknown in your text and then create an index on it. Or give it 0 or NA or something else. So that's because this statement here with the is null, this will be slow. So if you've got null values, just beware that you might have problems later on when you try and search for those nulls. Nulls don't mean anything, which means that you can't search for them. Okay? Alright, so now let's talk about indexes. So we created all the tables. The tables are like a book that contains all the information that we have. The index is like an index in a book, right? We use the index to look up particular pages in the book. We only use the index when we're looking for one thing or a few things. We don't use the index to read the entire book. So you never open a book, go to the index and start going through every index entry one by one and going backwards and forwards to the book. Never, right? If you want to read the whole book, you read it start to finish. Indexes are the same. You only use the index when you're looking for a few small things, a couple of pages, or if you're going to look for 3 pages, 4 pages, 5 pages. But if you're reading a whole chapter, you don't use the index. So you only use the index to search for specific things. The best thing you can do at this point to improve performance is to create the best set of indexes. You create concatenated indexes, which are indexes that have more than one column in them. What happens, I see a lot of people with their first indexes, they make a mistake that they create indexes on every single column. And that's really bad. It actually slows things down and those indexes aren't very good. You want to create an index that has all the columns that you're searching for, and I'll show you in a minute how you do that. And remember too, indexes slow you down when you're putting the data into the database. It speeds up getting it out, it slows it down putting in. So don't create too many indexes. So as I said, a concatenated index has more than one column. So this is a concatenated index. 3 columns: surname, first name, date of birth. Guy Harrison, 21st of June, a long time ago, right? That's an index that has 3 columns, and that means if you look for me and you know my date of birth and my first name, it will be very, very fast, because there's probably only one Guy Harrison born on my birthday. But if you just create an index on Harrison, in Australia there's lots of Harrisons and it might be slow. So that's why you put all the columns in the index together. You create indexes on groups of columns that appear together in the SQL statements. You can still use this index to look for Harrison. You don't have to say Guy. It will still work on Harrison. You can't use it to look for Guy though, right? Because you have to specify the start columns in the index. Okay? So this index can be used to search for surname, but it cannot be used to search for first name. So let's have a look at what sort of differences you get with concatenated indexes. The more columns you have in the index, the less disk I/O you have to use to get your data. So here's an SQL statement looking for Connor Bishop, born in 1976, and we want their customer ID. If we don't have an index, that's how much I/O we have to use. We have to use 1500 I/O. With an index just on surname, it's 60 IOs. If we add first name, it's 6 IOs. If we add date of birth, it goes down to 4. And we can even add the customer ID into the index and save 1 more IO and go down to 3. So that's a big difference, right? That's 1,500 IOs down to 3 IOs for the same SQL statement. If you create the right index. If you create the wrong index, it might get a little bit better, still better, but you haven't gone as far as you can. This is why it's important to put all the columns in the index. The people, is that sort of okay? Do you understand what I'm saying? Okay, I hope so. Okay, we've said that. And then that's another point. If the index has all the columns in it, maybe you don't have to go to the table at all. It's as if you looked up the back of the index of a book and you found exactly what you wanted. You were looking up, it said, you know, Guy Harrison born in, you know, 1960 or something, and you found, oh, I don't have to go to the page. The index has the information I want. Now this is what happens as you add more indexes and you're inserting data into a table. So indexes speed up the queries, but they make inserts and deletes and updates much slower. So here we start with just one index, and this is how much IO it took, 1,200 IOs. 2 indexes, 3 indexes, 4 indexes, 5 indexes. We get up to 7 indexes and we're more than 10 times slower at inserting data. So the indexes have a big cost, and you have to balance the cost of the index. The index helps you speed up your reading, but it slows down your writing. And it's hard to know how many to create. But for me, I usually worry if there's more than about 4 or 5 indexes on a table, maybe even 3. Okay. I'm going to just skip that one because I think we don't need that. Okay, so now that we've created all our tables and our indexes, it's time to write the code that is the application, right? This is the fun part, right? Everyone likes writing code. Boring to create tables, fun to write code, hopefully. I like it. So when you're writing code against a database, you have a couple of things that you need to keep in mind. First, don't talk to the database unless you have to. If you've already asked the database for a piece of information and you know it's not going to change, don't ask it again, because every time you talk to the database it's expensive. It's your round trip to the database server, it's I/O, it's all that sort of stuff. And then don't execute the same SQLs twice if you don't have to. This is done using a thing called bind variables. Then your transaction design, make sure you don't hold locks for a long time when you're writing your code. I'll show you what I mean in a minute. There's a thing called optimistic and pessimistic locking, which is important to understand. And then don't use up too much network bandwidth. As you're going backwards and forwards to the database, there's ways you can be very efficient in that. So SQL execution. Don't send a request to the database unless you have to. Particularly if you can remember what the database has already told you, that's better than asking the database again and again and again. And also don't create a brand new SQL statement just because a little bit of it has changed. So here's an example of a caching. It's best to avoid asking for the same data twice. One way to do this is to keep the data that you get in variables or in an array. So this is PLSQL code. It's Oracle's stored procedure code. And in this code, we're remembering what the database tells us. This code looks for a product. You give it a product ID and it returns the product price. And here, before we even look to the database, we look in our array, our list, our collection. And if we find the product in our collection, we don't go to the database. If we don't find it, we go to the database, we get the product price, and then we put it in the list. It's simple as that, right? It's just creating a client-side cache that you can use to remember what the database has told you. Now, you have to be a bit careful because maybe the data is changing and you don't want to ignore those changes. But this sort of technique goes a long way to reduce the load on the database. The second thing that you can do is not create a new SQL statement every time you send change the query. So here's some Java code, and you can see in this loop we're calling this SQL statement every time inside the loop, right? It's a new SQL statement. Each one is different, and we open it, we execute it, and we close it. And so every time inside this loop, we're sending more and more SQLs every time. There's a much better way to do this in Java and C# and elsewhere. You prepare the statement, and then you execute it multiple times with different parameters. So this is how the good code looks like. We have a prepared statement, we get it ready. The bits that are going to change, this part, the variable part of the SQL, we create a placeholder for, or a bind variable. And then every time we execute it, we set the value before we execute. And so it's a little bit more code, it's a little bit more complicated, but it's much, much faster. So here's how much faster it is. This is the first piece of code, and this is the second piece of code, executing 1,000 times. It can be a lot faster if you use prepared statements in Java or the same sort of thing in C#. Okay, so on to locks. When you change any piece of data in the database will lock it, and no one else can change it until you issue your commit. Probably everyone knows this, right? You change some data, until you issue commit, that data is locked. You want to make sure that you are holding those locks for a short period of time. While you're holding that lock, other people can't get work done. So you want to make sure that you're releasing the lock as soon as possible. There's two ways to design your code to hold locks. The first way is called pessimistic, and it's called pessimistic because it means you feel that someone else you're worried that someone else might come and get the row before you change it. So you want to lock it early. The other way is called optimistic. You know, optimism, you know, you're looking to the future of your code and you think it's good. No one's going to come and get your data, so you're going to leave it. You're not going to lock it. You'll leave it till the last moment and then lock it only if necessary. So this is how the first one looks. Pessimistic. Pessimistic, we lock the row first, then we do all the things that we do, then we commit. Optimistic, we don't lock the row, but later on, just at the last minute, we go and see if the row has been changed. If it's been changed, we have to go back to the start because we didn't lock it. You know, someone else can change it underneath us. So, but we're optimistic. We don't think this will happen. If it hasn't changed, then we can commit. And you can see here, this is the duration of the lock on this side. On that side, the duration of the lock is much shorter. So optimistic locking is good as long as people aren't really going to change the row underneath you. If they do change it, then it's too bad, right? You have to keep going back and retrying, and maybe you'll get slower. So that's optimistic and pessimistic. But we like, from performance, we like optimistic. So reducing network traffic. Every time you go to the database, you send a packet across the network to the database server and it comes back. And all of these round trips to the database, you know, go to the database and come back, all takes time. And so there's two ways to reduce the amount of going to the database and back. First way is called array processing. And this is just when you're getting data from the database, pull out all the data in one operation. Don't do 1 row, 2 row, 3 row, 4 row, 5 row. Do 1,000 rows all at once. And it really reduces the amount of network traffic. So here in Java, it's very easy. It's this, set fetch size is the number of rows that will come across in one operation. In C#, it's this, fetch size, it's in bytes. So that's in rows for Java, it's in bytes for C#. And each language is a little bit different like that. But when we increase the fetch size from 0 or 1 up to 100, you see the time it takes drops really, really quickly. It's a really big deal to use array fetch, right? Here at 20, we are already 6 times faster. And if we get up to 60, we're maybe 20 times faster. So always do that. It's very easy. It's harder to insert in batches. It requires more code. So this is some code to insert in a batch. You write your SQL statement, a prepared statement with placeholders like that, just like before. And then when you execute it, you add to the batch. And then when you're ready to insert your batch, you execute your batch. So it's a bit more complicated than the one row at a time, but it's just as much faster, right? If we do it one row at a time, inserting rows, it takes a long time. If we insert in batch, it's pretty quick. So you should do that. Okay, and the other way to do network is stored procedures. So if you think of a transaction that does something complicated with the database, it might go backwards and forwards quite a few times. So this is one going to the bank. And so we go to the bank and we look in, we're transferring money. So we go to the database and look in the money in one account, then we look in the other account, then we check withdrawal limits, then we issue an update, then we issue a check, and then we do a commit. And that's like 5 or 6 or 7 or 8 times we've gone to the database, come back, go to the database, come back. If we write a stored procedure, code that runs right inside the database, we just have to go to the database once. And so is this important? It depends if you're going across a slow network. Here, we're going on the same machine. And it doesn't, here in the green one, it's the same machine. It doesn't make much difference. But the blue one, where we're going across the network, you can see the stored procedure is a lot faster. So sometimes when network is a real problem, you will want to write your code as a stored procedure. Okay? And that in Oracle, that's PLSQL. In SQL Server, it's T-SQL, and in MySQL, it's just called stored procedures. Okay. So we've still got a few minutes. So we'll go into SQL tuning. So the SQL statements you write tell the database what to do, but they don't tell the database how to do it. The database compiles the SQL statements into a thing called an execution plan, which is how it's going to get the data. A lot of times the database gets the plan wrong, and so you have to fix the plan for the database. The optimizer is like the runtime compiler for the database. It takes the SQL and works out what to do with it. So which table will I get first? Will I use an index? What's the best index for me to use? All the decisions the database makes are made by the optimizer. Your job is most of the time to help the optimizer by giving the optimizer the right information about tables and how many rows there are and so forth. Then you have to look and find the SQLs that didn't work, and then you have to sort of fix those SQLs, and there's a number of different ways, but usually you might have to rewrite the SQL or add a thing called a hint. So as I said, the optimizer works out the cost of each plan, and to do that it has to work out how much data is going to be processed. It gets this from table statistics, and then it works out how much CPU and I/O. This is an execution plan. This you see this in sometimes it's called a query plan, explain plan, or execution plan. Here's the SQL statement. This is what the optimizer is going to do to go and get it. It says here I'm going to read this table, then I'm going to sort it, then I'll read this table, then I'll join these two things. This is our 10-minute break?
Yeah.
Okay, so we'll come back in 10 minutes and keep going. Thank you very much.